A function is continuous when you can draw it without lifting your pencil. If a function has a hole or a jump, then it's not continuous. More formally, a function is continuous at x equals a if the limit as x goes to a of f of x is equal to f of a. For a hole, the limit exists but the function value isn't the same. In a jump, the limit just doesn't exist. In general, a function is continuous on its domain. The big exception is piecewise functions. Here's an example. Determine when the following function is continuous. This is a piecewise function. You should check that each piece is continuous. The bottom piece, 1 over x, is not always continuous. It's bad at x equals 0. But this doesn't actually matter here. This piece is only active when x is larger than 2. Now check the breaks in the pieces. I'll draw a quick picture to demonstrate these breaks. At each break, take the limit from the left and right. Approaching x equals 1 from the left, the function looks like x, so the limit is 1. You can get this just by plugging in 1. From the right, the function looks like x squared, so the limit is also 1. Therefore, the limit as x goes to 1 of f of x is 1. Finally, f of 1 is also 1. Therefore, the function is continuous at x equals 1. The other break is at x equals 2, and there's clearly a jump discontinuity. You could formally go through the limits here too, and it's good practice, but just look at it. It's a jump. It's discontinuous. This brings us to the intermediate value theorem. This is arguably the most important theorem in this course, definitely top 2. The intermediate value theorem says, suppose f of x is continuous on the closed and bounded interval a to b, and f of a is not equal to f of b. If n is between f of a and f of b, then there is a c between a and b so that f of c equals n. There are 3 essential assumptions: continuous, closed, and bounded. Each of these is necessary. Missing any one of these causes the intermediate value theorem to no longer hold. Let's play a little game. Draw this picture. Draw a horizontal line anywhere between f of a and f of b. Mine will be right here. You want to connect this dot and this dot without crossing the line. Try it. You'll quickly find you can't, and the reason is the intermediate value theorem. You're drawing a continuous function on a closed and bounded interval. You must cross the line. The x value at the intersection is the c as guaranteed by the intermediate value theorem. Your c value is probably in a very different location than mine. That's because the intermediate value theorem only says that c value exists. It doesn't tell us what it is or how to find it. In fact, we don't know how many c values there are. There could be multiple. It's also possible a function goes above and below the bounds, but it's not necessary, and that's why n must be between f of a and f of b. Here's a question. Does 2 to the x ever equal 3x? There are many ways to answer this question. You could graph both curves and see if they intersect. But what if you wanted an approximation? I guess you could use the graph to estimate where they intersect, but that's not really going to be an accurate estimation. What if we wanted that approximation to be really, really precise? You can actually use the intermediate value theorem for this. Get this thing equal to 0 and set f of x equal to it. The idea is that we're going to find an a and b so that either f of a is less than 0 and f of b is greater than 0, or vice versa, f of a is bigger than 0 and f of b is less than 0. If we can do this, then between a and b, f of x will equal 0 somewhere. Just start trying points. If x equals 0, then f of 0 equals 1. If x equals 1, then f of 1 equals negative 1. Well, that's a freebie. We just found our bounds. Then 2 to the x equals 3x for some x with 0 less than x less than 1. But 0 to 1 is still a very big range. Why don't we try to half it? What is f of 1 half? It's minus 0.08. This means 2 to the x equals 3x between 0 and 1 half. We can split the interval again, so the solution is between 1/4 and 1 half. And again, then it's between 3/8 and 1 half. And you could keep doing this until that interval was as tight as you wanted. The tighter the interval, the better the approximation.